Continuing with Chapter 6. Last time I just did a short introduction to Chapter 6, talked about shearing stress, and the main point that I wanted you to take away is that the equations that we have so far for shearing stress talk about average shearing stress, which is not an adequate value for design. So we need to find shearing stress at every point on a cross-section and also across an axis. And because shearing stress tends to concentrate rather than distribute, we need to have better techniques and more precise math for finding those values. So there are two ideas that I want to present first, and then we're only going to talk about two geometric shapes. But the two ideas, when we talk about shear concentrating rather than distributing, the first is called shear flow. And what this basically means is that if you have a beam like this and you subject it to some vertical load, that the beam is going to bend in this type of a configuration, more or less, and that the shear is going to flow across the axis of the beam, or move. You can think of it as a fluid moving over the beam. And also, if you look at the cross section, that the shear will flow down and across the beam. Now, and of course here at this edge it's going to be different, but if we're talking about a cross section here. So the basic thing is the idea of shear flow, which we define, or the variable that we use for shear flow is little q, is equal to something about the shearing force V and something about the first moment Q and the moment of inertia I. Now, in terms of Q and I, these are both functions of the shape of the cross section and Q, which we're going to break up each of these very, very finely. We're going to define them mathematically so that you're able to find out what they are. But Q is also a function of the location of a point from the neutral axis of the cross section. So the first thing I want to do in order to concentrate our discussion is that we're only going to look at two cross-sectional shapes. So you have to learn these shapes, and this is what your homework will be on and what your test will be on. And then if you are working in an industry where you have to do this, you're going to have to go back and find Q and I for more shapes than we are going to be talking about. But the two shapes that we will talk about, and we're talking about cross-section, is a rectangular cross-section and the cross-section of an I-beam. We talk about this because there's quite a lot of symmetry and it's relatively easy to analyze. And we talk about this because an I-beam is such a common building material. Okay, so those are two things that you really need to do. So we're going to talk about what Q and I are for different building materials, or different shapes of building materials. Now, the other thing I would like to say explicitly, it's not implied in this equation except by the fact that the variable little q and capital Q are used in the same equation. These two variables, even though we have the minuscule and the majuscule version of the variable, they are not directly related to each other. They do not describe the same property. okay? Little q, shear flow, is a, it's a property of stress per length. So in other words, we're talking about how stress moves from here to here across some length, which we could just call delta x. Okay? And, hang on just a second. And capital Q is a geometric property. So the units aren't the same, and they're only related because they're used in the same equation, but one is not a direct function of the other. This is a function of the length along the axis, possibly the placement of fasteners, and the amount of shear that's applied. Q, on the other hand, is directly a function of the shape and size of the cross-section and the point that we're interested in doing analysis for. Okay, so this is the first equation. Little q, shear flow, is equal to VQ over I. The second equation is for shearing stress, which is directly related to this equation for little q. Shearing stress tau at a given point is equal to V times capital Q, that geometric property, times I over T, which is the thickness of the place in question. So whenever we find the shearing stress on a cross-section, it's going to be different at every point. So the stress here is actually going to be the same, but I'll describe this in a minute. So this would be like tau A, and this would be tau B. Over here, you would have a different stress here, as you would here, as you would here. Okay? So you can call that tau A, tau B, and tau C. And what that stress is going to amount to depends on where you are, as well as the size and shape and the amount of shear that's applied. Okay, so V, as we've said, is the shearing force. So that has dimensions of force. In other words, it could be pounds or newtons. Q is the first moment of area. We talked about this a little bit, but we're going to cut it up so you know exactly what we're talking about. But the first moment of area about the neutral axis. I is the moment of inertia of the cross-section. First moment of area about the neutral axis on the cross-section. There we go. I is the moment of inertia of the cross-section about the neutral axis. And T is the thickness of the cross-section at the point in question. So if we look at tau A, for example, I'm going to look at tau B rather. Let's look at tau B right here. If we look at tau B, V is going to be a given in the problem, or some sort of applied load that we can calculate for. Q would be the first moment of the area above point B about the neutral axis, which we're going to describe in just a minute. I would be the same everywhere. I is the same at point B, at point A, at point C. And V is the same everywhere. Q is not equal to, the Q at point B is different than the Q at point A, which is different than the Q at point C. So we have to determine what those Q values are. And generally speaking, that's the hardest thing to see. I have to draw a picture, I'll show you how to do it, no problem. And then the thickness is how wide we are at that particular point. Now, generally speaking, you choose the smaller of the dimensions. So for example, if you were looking here at point B and you thought, well, do I choose the direction X or do I choose the direction in the Y? Because X is smaller, you choose that. The reason is, has to go back to that idea of shear not distributing. It's, if you have a smaller thickness, that's where it's going to concentrate. Because if you look at the equation, VQ over IT, the smaller T is, the bigger tau is, right? And that's what we want to design for. All right. So let's talk about finding I for my two shapes. I have a rectangle. I have an I-beam. Okay, so we're going to go through the derivation for the I-beam, but then you'll know what it is. So you just use that in the future, okay? And then Q is not something we can do quite like in 2 steps, but I'll show you how to do that. So I have a rectangle. About its neutral axis is 1/12 times the base times the height to the third, every single time, okay? So you have a rectangle like this. It has a base of 3 inches. It has a height of 4 inches. The I that we're going to use in our equations, I sub r, would be 1/12 times 3 inches times 4 inches raised to the third power. 3 times 4 is 12, so that cancels against 12. So in this case, that would be 4 squared, or 16 inches to the fourth. Right? So you always use this formula if your cross-section is a rectangle. If your cross-section is an I-beam, you will always use a formula that I'm going to derive for you here. And this is based on the parallel axis theorem that you learned in statics, which I'm sure you're all just totally familiar with. It's just like that. All right, so the first thing is we have to determine the neutral axis. For a rectangle, by symmetry, we can find that the neutral axis is just in the middle. So in other words, if this is 4 inches tall, this is 2 inches, and this is 2 inches. That's not particularly important to the discussion of determining the moment of inertia, but for an I-beam it is. So an I-beam, the only type of I-beam that we're going to talk about is a symmetrical I-beam. In other words, the upper part and the bottom part are the same size.
They're non-symmetrical I-beams?
Sorry?
They're non-symmetrical I-beams?
Yeah. Oh, yeah. Absolutely. Good question, though. Yes.
Curious.
I know. It's weird, huh? Yeah, they make, yeah, a lot of times they do that. So I just want to show you a picture of an I-beam here. Probably would like to see this, if my screen will come up. Okay, so here we look at just a basic shape of an I-beam, and they're just used, like we said, in all kinds of building materials. The parts of an I-beam are called, the flange are the wide parts, and the web is the slender part in the middle. Now, in real life, they tend to be, if they're they're usually cold rolled, so you get sort of a curved surface here. We're really not going to talk about that sort of I-beam. We're going to approximate our I-beams as 2 rectangles for flanges joined by a rectangle in the web, and we're not really going to talk about the curves. Now, if you do have a rolled section, you can use the charts in the back of your book to get the eye of the I-beam. I never thought about that before. You need to use the moment of inertia of the I-beam, but that's not going to be necessary in this class. What you will see, should you decide to look into this, is that if you use the tabulated value of the moment of inertia for an I-beam about its cross-section, it will very closely approximate the formula that we're going to do in class for a squared off I-beam. Okay, so let's come back over here to the document cam. So what we're going to talk about then, when we talk about the eye of an I-beam, the first thing is we're only going to talk about symmetric, so that the neutral axis is in the middle. So when when the I-beam is symmetric, that means that we could basically fold it over on a horizontal axis, and that the edges of the upper part would exactly match up against the edges of the lower part. And that means that the neutral axis will be directly where that fold occurs, where we have an axis of symmetry. So basically, let's say to calculate, we need some dimensions, and I want to make this so that it looks the same every time. So we have a flange and a web. Okay. So the other thing about a symmetric I-beam like that is if you look at the web as being a rectangle, the neutral axis of the web is exactly the same as the neutral axis of the entire I-beam. So that means that we can first say, when we're talking about the moment of inertia of the I-beam, about its neutral axis, that the web is already in place, and we can just use 1/12 times the base of the web times the height of the web raised to the third power. But now we have to talk about the flanges, and to do that, the neutral axis of the flanges are going to be halfway through the flange itself, because if we folded the flange over on itself, the axis of symmetry would be right in the middle. So that means that we need to use the parallel axis theorem to move our moment of inertia from the centroid of the flange, or the neutral axis of the flange, to the neutral axis of the I-beam itself. So for one flange, that means that we're going to have to take the centroidal moment of inertia of the flange and then add to it the moving term, which is AD squared. The parallel axis theorem says that to move I to a new axis, it's equal to I prime plus AD squared. Okay? Once again from statics. So the area of the flange is the base of the flange times the height of the flange, and the distance from here to here is going to be half of the height of the web plus half of the height of the flange, right? So AD, which is, actually I could do it another way, but let me think about this for a second. Half, I would like to say half of the entire I-beam plus half of the flange, or minus half of the flange. But I could also say 1/2 the height of the flange times the height of the web, area D, quantity squared, right? And since this and this are the same, there are two of those, right? Because whether it's above or below the neutral axis, because it's always D squared terms, the I-beam contributes the same whether it's below or above. If you recall, the integral equation for I is y squared dA. So if area is positive, y, whether it's negative or positive, y squared is positive as well. All right, so if we simplify this, we can say then that the I of an I-beam is equal to 1/12 times the base of the web times the height of the web to the third, plus, I would like to see if I could simplify this just a tad, 2 times 1/12 times the base of the flange times the height of the flange to the third, plus this is this times this, AD, there we go. That has to be added. Gosh, I don't really see any way to make this simpler. Oh, I've got it. This is 1/12. This is 1/2. Base of the flange, height of the flange, 1/2 base flange times the quantity height of the flange plus height of the web, quantity squared. Okay. Now there's probably a simpler way to write that, but I think all I'm going to do here is just divide through or multiply through by my 2. So I could say in final form that this is 1/12 times the base of the web, height of the web to the 3rd. I'm going to multiply this through, it's plus, this quantity becomes 1/6, base of the flange, height of the flange to the 3rd. When I multiply this through, the half goes away, plus base of the flange times height of the flange times the quantity, height of the flange plus height of the web squared. Okay? I guess I got rid of that parentheses when I did the work. Okay? So there's the formula based on the dimensions of the I-beam. Now, I feel like I could simplify this a little bit, but it feels like maybe I could pull out the base of the flange, the height of the flange, but I really don't know if it's going to make the equation any simpler. Okay? So that's geometrically what you'll need to use. So if you have a rectangular cross-section, use 1/12 base height to the 3rd. If you have an I-beam, you keep in mind the dimensions of the web and the flange and use that equation. And those are the only 2 that we're going to use in this chapter for our work. Keeping in mind that when you're practicing engineers or when you take mechanics and materials 2, you may have to expand your repertoire of moments of inertia. But for here, this will do.
The second one?
Uh-huh.
What happened?
What do you mean?
You teach
No, I would love to teach it. I would love to teach it. It's a junior level class, so you have to take it at university.
it? How is it fun?
Of course it's fun. It's great. It's more about real, we're learning such principles in here, such foundational stuff. And when you get into mechanics and materials too, you'll get into more real world stuff. So more.
Actually, I can't stand principles, and that's all I've been learning for 2 years.
Well, it would be interesting to ask Christian this question or to have a discussion with you. In the United States, we just don't concentrate on sciences and maths very much, and so we spend 2 years basically teaching people like how the real world works. I don't know if it's that way in other countries or not.
No, we just do it.
You just start doing it at the beginning. Yeah, that's what I was afraid of. So that's why engineering school, the first 2 years of engineering school is like just principle, and reinforcing. Like I was saying, if you're in if you're in physics 2 and it doesn't make all that much sense, then you take electric circuit theory and you're learning the same material from a different angle, and then it reinforces so that you get it, so yeah.
I talked to my coworkers with German yesterday.
Yes.
That they had this stuff in the first semester.
See, there you go. Yeah, in the first semester of engineering school. Yeah, see, and that is very interesting to me. I mean, I wish we were there, but we teach a little bit. Our K-12 education tends to be a little bit
On the soft.
soft or broad is what I was going to say, but yeah, I think, I could have some other discussions about this too, but it's all philosophical.
Yeah,
So we learn it. We're learning it here.
But on university, it's like 50% does not pass the first semester.
Right. 50%, even after they've had that solid educational background. Yeah, in engineering here, for the undergraduate degrees, typically speaking, 1 in 4 people who starts as an engineering major will complete a 4-year degree in engineering. Now, when I say that, you guys are already way past the hump, because what I see is that 3 out of 4 drop out before they can really get through calculus and statics. So I think the numbers of people who are successful go up by the time you actually see somebody in an engineering class. So, so I'm confident, and I would not say this, I'm looking at each of you as I say this, I'm confident that everyone in this room has what it takes to do the job if you want to finish it, so, and I've not always said that to everybody. I want to let you know, I have occasionally had to say to people, have you thought about something else? So,
It's a nice art degree over there.
what's that? Yeah. There's this degree called humanities. No, I'm sorry. The humanities. Anyway, no, that's bad. But yeah, it's not, and so philosophically, now that we've got all this down, my opinion is that if you're suited to study engineering, nothing else will ever be as satisfying. But it's not for everybody. So, but I find for myself that taking classes in other areas can be not as exciting, not as engaging to me, and I know I've mentioned several times my youngest son, he's in a graduate program at University of Wyoming, but he graduated in mechanical engineering, and this year he's doing 2 master's degrees. He's doing one in business and one in engineering. It's a co-program, but his first year is all business. And he called me Sunday, and he's a hard worker, just like you guys are. I mean, it's not like that, but he's just like, really, I just feel like I'm making stuff up all the time, And so it's just, so there's a little bit of that, I mean, what we do in here is pretty solid. And so I think it's exciting. I think it's exciting because you learn how things work, So what would be more interesting than that? All right.
Learning how things don't work.
Well, that's equally as important. We have to, sometimes we have to dispel notions, I mean, sometimes we have to, sometimes people come in with some interesting ideas, and unlearning things can be a problem. So anyway, but yeah, it's kind of fun. You know what? I'm going to stop here today. When we come back on Friday, we're going to discuss the mystery of the large Q, and we can go from there. So anyway, that's it for today, ladies and gentlemen. And I'm not ready to give you any homework yet, so finish your homework for the previous chapter, and on Friday we'll continue, and we'll get all of our variables broken down. The only variable we have left to break down really is Q, capital Q, and then we will continue our discussion of solving problems to find shear stress at particular points. There we go.